Good afternoon to everyone. I am Andrea Chiocca. I'm a researcher from the University of Pisa, and today I would like to present an ongoing work about the development and application of the effective critical plane approach to some notch specimens and also some welded joints. So a little bit of introduction about fatigue, not so much. So we all know that usually the fatigue damage driver is not really the maximum elastic stress we can find, for example, on in a notch, but it's usually linked to an effective parameter, it can be an effective stress or similar, that is linked to a process zone in the material. And so if we want to use or develop a method or a model for fatigue analysis, then we have to consider the process zone in some ways. And so there exist a lot of methods in literature. Some apply to welded joints, some other more general methods. What we choose for this analysis are the critical plane methodologies, because we would like to have a background method that can account easily for multi-axial fatigue. So critical plane methods, probably you all know that, but it's a methodology that is not just evaluating an equivalent parameter, but it's also evaluating a critical plane or critical planes. So usually the critical plane is the plane where this equivalent parameter is maximized. What is the problem with critical planes? Is that the method is local. So usually you evaluate critical plane in a node of a finite element model. So you should account for material plasticity to account for the process zone. And also, to evaluate critical planes usually require quite a lot of time, because to be able to get the maximum parameter on the plane, you should at least scan a lot of planes in space, and this can be time-consuming. So a little bit of background about the methodologies we developed some years ago to speed up the evaluation of critical planes. The idea is not so strange. So we make use of invariants. So we define the fatigue cycle through range tensor definitions. We just subtract tensors that are defining two load steps, for example, the finite element analysis of a loading sequence. And then we use the invariants of our range tensor. It can be a stress tensor or a strain tensor. By evaluating the invariants, you can easily find the principal directions, then the maximum shear stress or shear strain, and so on, in a closed form. So we can find the equivalent parameter and the critical plane or planes. So in this way, now you have a closed form solution to obtain directly, without scanning the planes, the critical plane or planes. So this is an example. This is a hourglass specimen tensile tested. The color surface is the scanning plane in space, and the annular line here are the infinite critical planes you can find by closed form solution. This is working under any loading condition and material properties, so also including plasticity, when you want to maximize just the one parameter, like Fatemi-Sochi, the standard definition, for example. If you make the hypothesis of proportional loading and linear elastic material properties, then you can also find closed form solutions for those critical planes that require the maximization of the entire factor, like Findlay, for example. So this is an example. The dots are the closed form solution, and the surface is the standard way of evaluating the critical plane factor. Speed up any definition of critical planes, like Findlay, in under any loading condition and material properties, so also including plasticity. We should move from the analytical world to the numerical world. And so a way we found out was to, instead of searching in a 3D space or all over the surface, we just pinpoint the optimal path, and then we iterate on the optimal path to find the maximum. And in this case, you can speed up a lot the evaluation. So now we have some methods that offer a rapid way to evaluate critical planes. They are, easy to implement in finite element models or in post-process programs like Python, MATLAB, and so on. And they also provide a physical interpretation of what is going on with the critical plane factor, like, for example, finding infinite planes because of the definition of the Fatemi-Soci in this case, something that the scanning is not really providing. So that's so the first goal, but also there is a problem. So we can speed up a lot the computation. So these are notch components under multi-action non-proportional loading. This is a map of Fatemi-Soci. So the maps are the same, but with the method we implemented are different. So here it's just 1 minute's computation. Here are some hours of computation to find all the critical planes. The problem is that we just speed up the critical plane evaluation, but we still are evaluating the standard critical plane. So we should implement plasticity in this case. So can we use critical plane definition, but based on linear elastic finite element models? We tried. So this is the more or less the workflow. We would like to use linear elastic material properties, and the process zone is no more in the implementation of plasticity in the finite element model, but trying to average the tensor directly. So we do something similar to the strain energy density method, the average one, but instead of evaluating a scalar quantity, we still maintain the tensor math of our stress state by averaging the tensor around a volume, for example, spherical volume. So by doing this, you can evaluate a curve, that is this effective critical plane factor, as a function of the radius, so the volume dimension. So what we need now, okay, something we discovered that we didn't really think about is that even if the effective parameter is changing by changing the volume, the critical plane is not changing. So here you see the angles defining the plane. So usually you can define a plane by 2 angles. Here's for the definition of a Smith-Watson topper, here for Fatemi. So here you find 2 critical planes, here just 1. But the important thing is that by averaging under small volumes, the plane is not really changing. So you have an equivalent parameter that is changing, so taking care about the process zone without changing the critical plane. So the definition is still there. So the workflow we are using now is based on linear elastic models. We try to find this optimal control radius, so volume dimension, like the strain energy density or other methods similarly. To do this, we use, for example, some experimental data set, 2 fatigue curves, and we minimize the residuals of the number of stuff equal to failure, and then we define this optimal control radius. By doing this, we use some other experimental data to validate the method. So this is what I will explain later in the presentation. This is just an example of the calibration phase. We use, for example, a blunt notch geometry and a sharp notch geometry, fully reversed load, uniaxial loading. We find this curve of the residuals. We take the minimum, and then we define this as the optimal volume dimension for the material selected. This case was a low carbon steel, if I remember correctly. So let's go to the first case study. We found some data from a work of Professor Sussman and Professor Taylor. We have a data set of uniaxial loaded specimens. These are plate specimens with different notches, and a data set of multi-axial loaded proportional and non-proportional specimens with different notch geometries. So the method was calibrated using the all 8mm and the V-notch, uniaxially loaded, fully reversed, and then we applied, so we validated the method with all the other data set. This is the result. So all the colored points are the validation point, and the curve, the fatigue curve here is not the best fit. This is the curve with the scatter derived from the calibration. So they are not related, okay? And here's some comparison with other methods. So here we can see the expected versus the experimental number of soft cycle to failure. If we do the hypothesis that these points are normally distributed, then you can easily define a distribution of an error function. That is the, let's say, we can define as the logarithmic ratio of the experimental number of cycle to failure and the expected number of cycle to failure. So in this case, we can see that the method calibrated using 2 data sets is behaving more or less in the same way of the modified Wheeler curve method combined with the TCD. What is the difference is that here we have 1 calibration parameter. In this case, we have 4 calibration parameters. So I mean, quite a huge difference for the calibration phase. Another material was a GJS 600, so a ductile cast iron. This data were retrieved from a work from the University of Trento. In this case, the material is behaving completely different. It's quite fragile from a fatigue point of view. In this case, also, we have different geometries and different loading conditions. The method was calibrated using a blunt and a sharp notch of uniaxially loaded specimens under fully reversed condition. And these are the results in this case, as before. So the color points are the validation points, and the curve is not the best fit, but is the curve derived from the calibration in this case. So same as before, we try comparing the method to other methods. In this case, it's strain energy density and two effective critical plane methods. We see that in this case, the effective Smith-Watson topper is working quite nicely, mostly because the material is phenomenologically breaking. The breaking driver is the normal stress or normal strain. So it's behaving way closer to Smith-Watson topper than to Fatemi-Sochi in this case. So let's go to welded joints. So we tried applying this to the welded joints. What is the problem is that to find the control radius or the volume dimension, we should define, we should obtain some specimens from the material of the weld seam. And so we tried, but the easiest thing was finding some data from the literature, so from a work of Brown. And so we used two data sets in this case to calibrate the radius. One base material data set, so we performed this experiment in our laboratory, and a data set retrieved from the literature. Always we need to different a blunt and a sharp notch to calibrate, and validation was performed on some tube-to-plate welded joints, experiment made in our research group some years ago. So here are the results. You can see in blue is the calibration based on base material, and in red is the calibration based on the weld material. You see, of course, we have two different control radius. One is a double respect the other one. So we have a bigger control radius for the base material. We can also expect that. But we can see that all the calibration points are more or less in the same scatter band. So this is quite a good news for us. So if we try doing the validation with the welded joints, you can see here that also in this case, the loading conditions are quite different. We have uniaxial, multi-axial, non-proportional loading condition. And here you see the validation using the calibration based on the weld joints, the weld material, and the calibration based on the base material. So from a scatter point of view, there's not so much difference. But if we consider the design curve, and then we perform validation, we see that the scatter changes a lot in this case. So if we calculate the expected number of cycles to failure, the method works better using a calibration based on the weld material. So we could expect that, but is it behaving well or not compared to other, say, methodologies developed for welded joints? So here a comparison, we apply the peak stress method in this case, and we can see that more or less the effective critical plane is, in this case, based on Fatemi-Sochi, is behaving, say, closely to the peak stress method. And so what we are doing now is trying to enlarge the welded joints dataset. The huge problem is to retrieve the material properties for calibration. And another problem in this case that for welded joints, if you want to model the nominal geometry of the weld seam, it's impossible. So what we are trying to do is to try to insert the hypothesis of the sharp notch also in this method. So similarly to the peak stress and other methods for welded joints. So with this, I conclude the presentation. Just really a short conclusion. So we saw that this effective critical plane, that is just a critical plane that is averaged, is working quite nice compared to other, say, method developed for fatigue analysis. What is really nice that is based on critical planes. So you can apply it for multi-axial non-proportional fatigue. And in theory, you can also apply it for variable amplitude loading. So something we didn't do it, but we could do it in the future. And so the results for the welded joints are promising, but we still need to enlarge the data set a little bit more. So thank you very much. And I'm here for questions.